Hi folks, in this video I'm going to show you how I built my electric buggy from start to finish. I set up chapters in the video so you can skip to the drive footage if you've already watched the build series. If you haven't seen the series yet, I link to each episode in the video description so you can check them out if you want more details. There's 10 episodes altogether, not including videos of the tools that I had to make along the way, so I had to leave a lot of things out of this video. I should also mention that I'm working on a time-lapse video of me driving around the trails and back roads to establish the battery's range, so make sure to keep an eye out for that upload in a few days. I built the chassis out of ERW steel tubing. DOM is a bit stronger and preferable, but it's quite a bit more expensive. ERW works fine as long as it's not undersized for the job, so the trade-off for saving on cost is a bit more weight. I used 1 1/4" diameter by 1/8 inch thick tubing for the main tubes and 1 inch by 1/8 inch thick tubing for most of the braces. I bent the tubing using a rotary draw tube bender. This is the only tool that I had to buy, and only because I couldn't make the die myself. I put a link to where I bought it in the video description. I fastened a sheet of plywood at right angles to the top of my work table and marked the center lines for the tubing to establish the profile of the chassis, and used them for reference when bending and assembling. I welded the chassis together in 2 halves, then joined them with cross members and added the bracing. Everything is just tack welded with my gasless hobby welder at this point, in case I have to remove and refit something later. After the chassis was finished, I moved on to building the double wishbone suspension for the front and rear wheels. I used the entire front hub assembly from a Yamaha Banshee ATV for the front wheels, but I had to make custom rear hub carriers to hold the Honda CRV wheel bearings that I used for the rear wheels, which will match up with the CRV axles and open differential that I converted to a limited slip differential and installed later. I made the control arms out of 1" by 1/8" ERW tubing and welded large bushings to the arms for the rear wheels, and welded bungs to the front arms to receive new Banshee ball joints. I also welded bungs to the opposite ends of all the arms to receive heim joints for connecting to the chassis mounts. I used some cheap coilover shocks for both the front and rear wheels. They're definitely not the greatest, but they fit the budget and will work fine for now. The steering rack that I used is designed with a lower gear ratio for a faster steering input response than what you'd find in a typical passenger vehicle. I made a custom steering wheel in a separate video and bolted it directly to the steering column, but I added a hub later so that I could install the wheel with a pin and remove it quickly so it's not in the way when I'm trying to get in and out of the buggy. Once the suspension and steering was installed, I started fitting the powertrain components. I started with the Honda CR-V rear differential. As I mentioned before, I changed it from an open differential by adding a simple limited slip conversion kit that's available on eBay. For the cost, it works pretty good, as you'll see in the dry footage later. The motor that I'm using is the ME1616 from Mode Energy. I ordered it along with the controller, throttle, contactor, and charger through Fanny at Kelly Controller. It's rated for around 24 kilowatts continuous and 55 kilowatts peak power with liquid cooling, but I've got the current turned down to around 95% in the controller just to be safe, so the actual output is around 22 to 52 kilowatts peak. The ME1616 uses a sine-cosine signal instead of a Hall signal, so I ordered Kelly's KLS 8080 IPS controller to match up with it, which is installed later in the video when I wire everything up. I created a movable mount for the motor which bolts up to the chassis and allows me to move the entire assembly with a 1/2" nut and threaded rod to adjust the tension on the chain and lock it in place. I mounted the large sprocket hub to a custom hub that I made for the rear brake rotor, which will be stopped by 2 calipers. The sprockets are designed for a 520 chain, and I wasn't quite sure it could hold up to the torque from the motor. But after the initial stretch when driving it for the first couple of hours, it's been holding up without any issues since. I created most of the body panels by cutting and bending aluminum sheet with my custom built sheet metal brake. A lot of builders like to use ABS instead because it's a bit lighter and easier to work, and I've got a few pieces installed too, but I wanted a bit more protection for the battery modules in case the tire kicks up a boulder or a stick on the trail. I installed a bucket seat and a 5-point harness to keep me strapped in if I ever roll this thing. I chose a camlock style harness, but I'm now regretting it because all the dirt and rocks that the buggy kicks up can get in the crevices and jam things up. A latch harness is more suitable for off-road vehicles. Because there's no transmission and because they can be fun to use when cornering, I installed a parking brake lever. It operates 2 cables that are connected to the 2 rear calipers. I got the kit on eBay, but it's not very good. The guts in the lever tend to fall apart if I'm too rough with it, so I don't recommend using the same one. I just use it for parking mainly. The motor has more than enough power to swing the rear wheels around when I want them to. I use a small 8-inch radiator and fan kit for cooling the motor, which I got from electricmotorsport.com. It's designed specifically for cooling electric motors like this and works pretty good when coupled with a 4 to 10 liter per minute pump. I also made a simple reservoir for the coolant out of solid ABS pipe and a few fittings. The coolant is just a standard 50-50 glycol and water solution. The system only cools the motor though. The controller and the battery use forced air cooling. After all the components were fitted to the chassis, I broke everything down and cleaned it all up with grinders and sandpaper, rags, and mineral spirits to prep for paint. I just used a simple trim clad primer and Alice Chalmers tractor paint. Nothing fancy here. The battery is made up of 32 lithium iron phosphate modules that I custom made using 24 5500 mAh 32 650 cells connected in parallel for a total 3.2 volts and 132 amp hours each. And I sealed them in vacuum formed ABS cases using my homemade vacuum former. I put a link for both of those videos in the description as well. Prior to assembly, the modules were all cycled, tested, and bottom balanced in parallel. In the buggy, the modules are connected in series to provide 102 volts nominal to the controller, which converts it to three-phase AC for the motor. The controller itself needs to be powered by an isolated power supply, like a separate 12-volt battery or an isolated converter. The 300 amp daily BMS protects the battery from overcharging or over-discharging, but it doesn't really do a whole lot in terms of balancing because it's just a passive balancer. It only bleeds off a small amount of current from the module with the highest voltage while charging, but it's nowhere near enough to keep up with the current going in and give the other modules a chance to catch up before the cell over voltage protection is tripped. So I had my F-series charger from Kelly controller wired to output enough voltage to bring the battery's sum voltage up to around 111 volts, and that keeps the weaker cells from getting into the upper knee of their charging curve. There's less than 1% capacity beyond that point anyway, so there's no sense risking damage for that. A passive BMS like the daily is really just serving as an intelligent circuit breaker. That's why it's important to either top balance or bottom balance your cells before assembling your battery, because that ensures that they're going to stay balanced during their normal operating conditions. All lithium iron phosphate cells can handle charging up to 3.65 volts, but they'll all settle to a resting voltage of around 3.3 to 3.4 afterward. Once everything was wired up, I had to do a bit of programming to sync the controller and the motor together and get them performing like I wanted, which I explain in more detail in the wiring episode. Once it's programmed, it's ready to test.